What you're seeing on the screen is the world's slowest experiment aimed at measuring the viscosity of pitch. Pitch is theoretically a fluid with extremely high viscosity, billions of times more viscous than water, and yet it's faster than what happened. Mom says it won't take long. This experiment was initiated in 1927 by Professor Thomas Parnell, and since then, 9 drops of pitch have already been observed. The drops took between 7 and 14 years to fall, and fortunately, we can see one of them falling in the accelerated footage here. This entire experiment is one of the slowest things ever created by humanity, with a speed of only a few centimeters per year. And here I'll introduce the most important concept of this video. We will embark on a journey from the slowest experiment to the fastest speeds we have already achieved or intend to achieve with our human technology. But let's start from this simple drop of pitch at the University of Queensland and move towards the speed of light. So, the question is, how do we create things that move at speeds close to that of light? How can we reach the highest speed allowed in the universe? And it's worth noting here that light is literally the fastest thing in the universe. It moves at approximately 300,000 kilometers per second, or precisely at 299,792,458 meters per second. I love saying this number in full. For comparison, the fastest human on Earth, Usain Bolt, reached a speed of 44 kilometers per hour using only his own legs, decades of training, and a bit of genetic luck. This is the best humans can do using their own bodies, and it's only 1/10,000,000th the speed of light, which makes it quite clear how far we are from it. Our main limitation is that our bodies are not made to accelerate at extreme speeds explosively, and I mean this literally. One of the best ways to speed up is to use the power of explosions, and that's exactly what internal combustion engines do. In an internal combustion engine like those found in cars, some fuel, usually gasoline, is heated until it catches fire, and when that happens, the fuel expands, generating energy. The energy from the fuel expansion is then directed to something that can generate movement. In the case of cars, this energy is what makes the wheels turn. The highest speed achieved by a regular car is 480 kilometers per hour, or around 100 billionths the speed of light. And here you might wonder, how come a regular car achieved this speed? It was reached by the SSC Tuatara, which is a normal car. Now, what I wouldn't consider a regular car is the Thrust SSC. In addition to wheels, it has airplane turbines and consumes 18 liters of gasoline per second. It reached 1,200 kilometers per hour, or 1 billionth the speed of light. This car is basically a plane with wheels, but planes do have wheels, so what's really missing are the wings, and that's also what we need to go faster. Getting off the ground allows us to avoid friction with the ground, and that drastically changes how we have to accelerate. When you walk, you push the ground backward, and the ground pushes you forward through Newton's third law. But in the air, the only thing we have is the air. For a plane to accelerate, it needs to push air backward so that the air pushes it forward, and that's basically what turbines do. Turbines use the energy caused by combustion to spin, creating a strong airflow inside them, which is what results in the acceleration of the plane. And here comes the State Route 71 Blackbird, a reconnaissance aircraft designed to be able to evade missiles and anti-aircraft weapons, as you may ask, simply by going faster than the missiles, resulting in an aircraft capable of moving at over 3,500 kilometers per hour. There are few things in the world that require more speed than evading missiles. Another one of them is escaping the planet itself. The principle of operation of a turbine involves pushing the air from the atmosphere backward and thus accelerating forward. The more air is pushed, the faster you will go. However, the atmosphere's air is sparsely dense, especially at high altitudes. So, you need to move large volumes of air to go very fast. However, to leave the Earth, you need to go even faster than that would be possible with this. So, instead of moving the air from the atmosphere, a rocket carries propellant, which is a material that will be expelled at extreme speeds during the combustion process. And the crucial difference is that the propellant will be highly compressed, and it will be possible to carry a lot of it in a small space. This allows for the expulsion of large amounts of matter very rapidly due to Newton's third law. This results in extremely high speeds. In the case of the Saturn V rocket used to go to the moon, the speeds reached were approximately 25,000 kilometers per hour, or 0.00. Notice that I'm no longer talking in fractions, but in percentage of the speed of light, which means that we are getting there. Or being in space removes one of the biggest obstacles to increasing speed, air friction. Instead of relying on dramatically increasing our speed like a rocket, we can just create constant acceleration for long periods of time because without friction, nothing loses speed. And that's how the Parker Solar Probe managed to achieve incredible speeds. This probe's mission was to make a close flyby of the Sun, and just this goal alone involves a tremendous variation in speed. When a probe leaves the planet, it's still orbiting the Sun at 30 kilometers per second because that's the speed at which Earth orbits it. And for the probe to reach the Sun, we need to reduce that speed until it almost falls into it. A fact about the Sun: it's huge, with 99.9% of the mass of the solar system being directly attracted to it by the force of gravity, which can create extreme speeds. In the case of the Parker Solar Probe, the maximum speed reached was 400,000 kilometers per hour, or 0.004% of the speed of light. And currently, we don't have any space travel technology that can go faster than the Parker Solar Probe, unless you want to get a space tan. In the hypothetical realm, the trick to going faster wouldn't be to have lighter ships and move them for longer. There are two conceivable ways to do this. The first is nuclear rockets, and the second is to use space sails. Ships that will have huge sails hundreds of meters in diameter and will accelerate by being illuminated by the Sun and possibly by lasers emitted from the Earth. In the best-case scenario, these designs could reach approximately 20% of the speed of light as they move to other stars, which is an extraordinary effect but has not yet been achieved. If we really want to go faster, what needs to be done is, of course, to accelerate lightweight things for a long time in a vacuum. So we're going to forget about the science of space exploration and we're going to go back to Earth, or more specifically below it at the Large Hadron Collider. Hadrons are simply atomic nuclei, and the Large Collider, at 26 kilometers, is large and collides these hadrons at extremely high speeds. To do this, for circular particle accelerators, each larger than the last, are used. They are all basically the same thing but in different sizes, long tubes in which an extreme vacuum is created. The tube is surrounded by conductors and electromagnets that produce electric and magnetic fields. The electric field causes electrically charged particles like the nucleus of an atom to constantly accelerate, and the magnetic field ensures that the particle will bend around the circle without any problem. Each of the four main circles of the accelerator was built to use the last of them. The particles are accelerated more and more in each one until they finally reach the LHC, which accelerates them to a speed of 99.999999% of the speed of light. The goal of this experiment is to explore particle physics by making them collide with each other at this absurd and interesting speed, which is the physics of the smallest scales that enables us to achieve the highest speeds. If we ever dream of reaching other solar systems and perhaps interacting firsthand with life outside of Earth, we will need faster ships. But we have not yet reached the stage of putting our best designs into practice. Achieving speeds close to the speed of light is a challenge of external technology and engineering, and perhaps it is the greatest challenge that one day, with a lot of luck and thought, we will be able to solve. Thank you very much, and until next time.